So we started the recording. I think everybody can see, and I think I'll start the introduction now. So welcome everybody. I welcome you to our fourth bioelectrodynamics webinar. And I would like to announce that this webinar is supported by the Engineering in Medicine and Biology chapter of the Czechoslovakia section of IEEE, and also by the Czech National Committee of International Union of Radio Science. Before I introduce our today's speaker, I would like to announce some housekeeping points, and that's I would like to ask you all participants, not the speaker though, when the presentation starts, please switch off your video and keep muted during the talk. If you have any questions, please type them to the chat, or after the talk you can raise the hand or give us any signal and we can unmute you as well. You can ask it. So no questions during the talk, please. As you might notice, the lecture is recorded, and we will then, if everything works technically fine, we will upload all the recording to the YouTube, to the channel, so we can also find out thereafter. So the talk will be roughly 45 minutes, but we will give freedom to Jack to extend if something turns out to be interesting. And yeah, so with this, I would like to introduce Professor Jack Tuszynski. He obtained his PhD in condensed matter physics in 1983, which is interestingly, well, also my year of birth. So this is really experienced in the topics we are so interested in our research, that it's the microtubule electric properties. So Jack then, after getting his PhD at the University of Calgary, he was a faculty member at the Department of Physics at the Memorial University of Newfoundland. Thereafter, he moved to University of Alberta in 1988, and I understand that since the time from 1988, his track was bound to this university, and he's then ranked up to the rank of the full professor. And for 15 years, until 2020, he held the prestigious Allard Chair in Experimental Oncology. Jack Tuszynski is also a very active scientist, published so far more than 500 papers, 12 books, delivered more than 400 scientific talks. More than half of them were invited, and he's also active in patenting his research outputs, having more than 20 patents across the world. And his grants so far, his research were supported so far by more than 100 grants. And he's also editorial board of almost 30 international journals, including the Journal of Biological Physics. And I would like to highlight that his major thrust in the research is computational biophysics, particularly in silico drug design for cancer chemotherapy and applications. I guess from where he got so many insights into microtubule structure and function. So with this, Jack, the digital virtual floor is yours, please.
Thank you, Michal. Thank you, Daniel. Thank you for inviting me, and thank you for attending to everybody. And of course, good afternoon if you're in Europe, good morning if you're in North America. This, as Michal said, this will be a talk about some of the work we've done on mainly electrical properties of microtubules. There will be some interesting recent results reported to you on conductive ionic conduction, capacitance, electrophoretic mobility, and also delayed luminescence. And I will cover the work done in collaboration with several labs, 2 or 3 labs at the University of Alberta, namely Karthik Shankar in electrical engineering, Al Meldrum in physics, Frank Hegman in physics, and also collaborators in the US, Aristide Dogario at the University of Central Florida, and Chris Carlson at Harvard. So this is the menu. I will start, as some of you may not be intimately familiar with microtubules. Microtubules are very important organelles, protein polymer structures built by all eukaryotic cells for various important functions. The most visible functions, of course, are providing cell shape and rigidity. Then they are indispensable for cell division and making mitotic spindles. And this was the reason that actually I moved to oncology for 15 years, trying to find new drugs for cancer that would inhibit this function. But that's a topic for a separate conversation. Maybe in September in Prague, I'll talk about this, but not today. And then importantly, the third function is providing pathways for transport in cells, such as kinesin and dynein transport, intracellular transport in all eukaryotic cells. So this is another sort of cartoon representation of all these functions, and also providing supramolecular structures, as you can see here, various geometries in dividing cells, radially emanating from microtubule organizing centers, centrioles and centrosomes, and in ciliated cells and nerve cells, microtubules forming parallel bundles, some of which is sliding and due to calcium waves, they can be executing waves or beating, providing force and propulsion to cells as well. So incredibly versatile. And as a sidebar to this, I just want to mention that microtubules are also involved in a curious way in the COVID invasion. They are hijacked by the virus and utilized for invading the cell and hijacking the centrosome. But I will not talk about this again. This is just a note that the importance of microtubules goes well beyond what we know in connection with eukaryotic cells. So what is a microtubule? Well, it's built from tubulin dimers, heterodimers, alpha-beta tubulin, which are encoded by separate genes, form a dimer, which is a stable entity, and these dimers are building blocks of microtubules, as you can see here, forming these hollow cylinders about 25 nanometer external diameter and 15 nanometer internal diameter. And I want to point your attention to the C-termini, which are sticking out. So it's not a smooth cylinder, actually it's covered with these whisker-like structures, about 12 to 17 amino acid in size, and the length is about 3 to 4 nanometers, but as I will try to convey to you in the next few slides, there's more than meets the eye because the influence of microtubules is much greater than the size, and that's due to their electrical properties. So we've been studying for the past really about 15 years electrostatic and electroconductive properties of microtubules, and today I will focus on impedance, both real and imaginary. In the past, we've shown that they have very interesting transmission line properties, and now we're moving towards interaction with the electromagnetic waves with both visible and near visible light, and there are some interesting properties I'll report to you as well. I want to mention also the dynamics of microtubule formation, polymerization dynamics. It's called dynamic instability, and it's a process which is unique to microtubules. No other polymers that we know of have this kind of dynamic property, which also involves asymmetric properties of growth and shrinkage. As you can hopefully see, growth is more linear and shrinkage is catastrophic, and involves peeling off the entire protofilaments. And so there's a different architecture of these two processes. But as I said, today I will try to convey to you the amazing richness of electrical properties of microtubules, which most biologists are probably not aware of and maybe not even interested in. But as a physicist, I am very much interested in this property. And here, microtubules are shown, tubulin as a building block of microtubules is shown as an outlier among the family of proteins that we characterized, we collectively, the world, and the dimer's net electric charge in vacuum is about minus 50. It varies depending on the isotopes, but as you can see here, is really very, very negative compared to most other proteins. And of course, in ionic solutions, this is neutralized, and the permanent dipole moment of the tubulin dimer is also an outlier somewhere in the range of, depending again on the isotype, 1700 to 3500 dBi, which is very large for any kind of protein. So these properties play an important role. And on top of that, the structural role of microtubules and the arrangements of tubulin dimers with these electrical charges into cylindrical surfaces with hexagonal symmetry makes an important distinction. Microtubules also have polarity, both biological. There's a plus end, which is growing, and the minus end, which is less dynamic, and it typically binds to microtubule organizing centers. But also electrical. These two ends of microtubules form an axis along which there is an electric field. There's also electric field around. And then helical arrangement, as we argued in previous work, is conducive to generating solenoidal currents, ionic currents around microtubules, which could lead to also responses to magnetic fields. As actually was reported many years ago by the Taboni group in Grenoble, magnetic fields of sizable strength can align microtubules easily. So microtubules then form potential building blocks for more complicated systems in cells, as well as perhaps hybrid systems in nanotechnology in the future. And in the context of cells, of course, you saw that they are used to form axonemes and basal bodies and centrioles, as you can see here on the right, going from nanometer scale to microns and beyond. Even microtubules have a very long persistence length on the order of millimeters, so you can create very straight and very rigid structures based on them. Also, they can be interconnected by microtubule-associated proteins. Again, a separate topic I will not get into. But what I want to point out is what Michael Levin from Tufts University in Boston has been writing and talking about for years, that all of this needs to be taken in the context of ionic solutions in the cell. This is a table of typical ionic concentrations, potassium being the most abundant with roughly 140 millimolar concentrations. But this changes depending on the cell, depending on the environment, and depending on the state of the cell. On the left, I hope you can see the transmembrane potential, which of course is due to the ionic imbalances between the extracellular and intracellular concentrations. And for normal cells, quiescent cells, the range of transmembrane potentials varies from about 60 to 90 millivolts. But when you go to things like cancer cells, then there is a dramatic drop down to 30 millivolts, or even for ovarian tumors, 5 or 10 millivolts. So there's a huge difference. And that has an important aspect vis-a-vis microtubules, which interact with ion channels and cell membranes. But you have to keep, and we'll come back to it later, you have to keep in mind the concentrations of ions around microtubules, because as we found out from our experiments and simulations later on, the concentrations of ions change the actual properties of microtubules. So we see microtubules as electrical elements, but not in the sense of a typical wire or a metal plate or something like that, but it's something that is dynamically changing depending on the environment in which it's placed. So this is just a sort of simplified table of things where mechanisms that might interact with microtubules and the characteristic frequencies. Much of it is superficial explore. There's still to be done, a lot to be done. So I want to leave this as a maybe a guideline for the future. So in the past, we never published this result, but we did experiments which use high frequency ultrasound in the megahertz range, that allowed us to break microtubules actually with ultrasound. Then in this talk, I will show you some results in the kilohertz to megahertz range for ionic conduction. There also will show you some terahertz results from the group of Frank Hegman on conformational changes and distraction of microtubules with terahertz. And of course, there's the potential electronic, excitonic, and visible interactions in the hundreds of terahertz range. And all of this, by the way, will have to be revised when you make networks from microtubules, parallel bundles, or interconnected squares, or things like that. As you know, in electricity and magnetism, network geometry matters a lot. So this was the bioelectric circuit model, which we developed with Horatio Cantiello. At the time, he was at Harvard with the experiments he conducted and represented each tubulin dimer as an RLC circuit, actually. RC, but L occurs when you have potential for solenoidal flows. So that element is variable. But in general, we can say that because of the electrical properties of microtubules, they can perform also various functions vis-a-vis ionic concentration. They can attract and even trap ions. They can accelerate ions in a favorable direction. They can provide resistive aspects of obstacles to ion flows. And we can also see them as cylindrical capacitors by condensing some of the ions in their vicinity. And then finally, although not quite demonstrated yet experimentally, and I mentioned a few times already this helical conduction pathway leading to inductance, which we see, but this is not really super direct, so I don't want to overemphasize this. But for sure, they can serve the purpose of storage, electrical charge storage devices within the cell. So now let me switch gears and talk for a few minutes about some experiments we did, and the main person who deserves credit for it is Arat Kalra, my former PhD student now at Princeton, who performed these experiments with Dr. Shankar in the electrical engineering department. And this is the semiconducting characterization device Keithley, which was used to, in conjunction with nano-manufactured electrodes. On the left, you can see some microtubules imaged in the device and outside of the device. And then the electric field distributions. The electric field generated between the electrodes were somewhere between 2 and up to maybe 18 or 20 volts per centimeter, so not very strong. And then we measured the behavior of conductance at different tubulin concentrations. So tubulin was prevented from polymerization using colchicine, and then compared it to microtubules, which were stabilized with Taxol, and we compared it to the BRB4 solution. So this was a 4 millimolar ionic solution. So that's very low ionic concentration. If you remember, this wouldn't be physiological, but this allowed us to see signal compared to noise. And it wasn't easy at these low concentrations of proteins in the buffer solution. But what we saw was that conductance in these plots as a function of frequency, and that range from 1 kilohertz to about 1 megahertz. Conductance consistently of microtubules, solutions with microtubules was the highest compared to solutions with tubulin, and finally the solutions without the protein. So in this case, we can see that polymerization of tubulin into microtubules can be seen as a transition into a more highly conductive medium. In fact, at this low concentration of ions, because you have to compare it to the amount of buffer, which is, thousands of times greater than the amount of protein, and you achieve a 25% increase in conductance. So that's very significant influence of microtubules. So when you translate it into the actual values, it's like 1,000 times or 2,000 times greater conductance than the solution. In other words, these form microtubules in these kinds of low ionic concentration solutions form bioelectric wires. Then we moved on to actually increase the concentration of ions towards this physiological values, and this is this more simplified setup with 2 electrodes and a solution, and we, in this case, we actually explored networks of microtubules, not individual microtubules, which is still a distant goal. And here, 3 cases, we wanted to see how the number of microtubules changes the conductance and capacitance, by the way, both real and imaginary components of impedance. And you can see here we increased the concentration by a factor of 10 to the middle, and then a factor of 100 to the right-hand side. You have the scale bar of 100 micrometers. So these are long microtubules forming meshworks, actually. And the results were actually at first quite stunning to us. Namely, what happened is that microtubule increased capacitance, or imaginary part of impedance, markedly, especially at low frequencies. And actually, you could easily extract from it the value of capacitance for the meshwork, and you will see in a table in a minute. And this was greater than tubulin, which is unpolymerized. So this is the buffer solution is BRB80, yeah. So polymerization has a dramatic effect on capacitance this time, but remember it's physiological or high ionic concentration, as opposed to low ionic concentration, which led to high conductance. Now it's high capacitance, something else. But on the other hand, resistance, so real part of impedance, showed the opposite thing. So now at high concentrations of ions, we have microtubules being more resistive than the solution and being more resistive than tubulin. So you could see here the formation of microtubules from tubulin as a transition to high value resistors as opposed to conductors. Very interesting. And so the question arose, in a minute we'll get into it, what the heck is going on? And that's a table summarizing the second set of experiments, and we kind of extracted approximate values for it, canonical 20 micrometer microtubule, resistance about 2 gigaohms, capacitance about 2 picofarads, and impedance about 7 femtohenries. And with the errors and from this table, I don't want you, of course, to remember all the numbers, but what's amazing is that increasing the number of microtubules does not appreciably change the value of capacitance, CMT, or in fact resistance. So this is what happens when you create networks. This is not easily predictable, especially, I would call them disorganized networks. Maybe not random. I'm not quite sure if random is the right word for it, but meshworks. Okay, so this is the summary. Microtubules at low ionic concentrations decrease solutions impedance, increase conductance. At high ionic concentration, they increase impedance, decrease conductance. And again, this is kind of a summary. We compared it to previous extrapolated values and compared to previous predictions. And now, of course, everything depends on 2 things, actually 3 things. The length of a microtubule, the concentration of the solution, and the arrangement of the network. So you can manipulate a lot of things. I think this could be the basis of future bio-nanotechnology by creating logical networks, circuits with these structures. And then just by naively calculating the resonant frequency of these from LC values, you get something like 650 gigahertz, so 0.5 0.6 terahertz maybe, but it's concentration dependent. We'll come back to it. So now let's move to terahertz, because let's go back for a second. This is where it's now bordering on the terahertz range of things. And so my colleagues in physics, Dr. Heckman and Cam Howe, his student, examined terahertz effects on microtubules. And terahertz has many in mechanism of interacting with biological material, including various water oscillations at different ranges of terahertz radiation. But terahertz radiation also introduces changes in protein oscillations, and affects hydrogen bond stretching and torsions. So a lot of things happening here, including proteins, DNA. But here we focus just on microtubules, and this is the intense terahertz pulse that was used, lasting on the order of picoseconds, 1 picosecond or so, and pulses were separated by milliseconds, and also different frequency was utilized, as well as broadband pulse with about 1.3 terahertz peak frequency and broad bandwidth on this order. This spot that was illuminated by terahertz radiation was about 1 by 1 millimeter squared or so, and different filters were used to create various frequencies from 0.5 to 2.5 terahertz, and here you have the results. On the left, you see microtubule networks, meshworks that we used for previous experiments. Terahertz off, pretty stable. This is over half an hour. On the vertical axis, you see the timeline from 0 to 30 minutes. Not much happening there. And then on the right, you have terahertz on. So over 30 minutes, you can see distraction of microtubules, so dissolution, and even some here on the right in the bottom corner, you can see breaking of microtubules into pieces, an image created from that experiment. And here's a video snapshots over 15 minutes. You can see dissolution of microtubules. Yeah, it's a wraparound, it's repeating itself, but it covers 15 minutes. Yeah. The problem here was that this wasn't 100% reproducible, and I think it has to do with the amount of energy that needs to be delivered. The intensity of the field needs to be about 500 kilovolts per centimeter. We've done some computational work with Dr. Cifra's group, and that came out of that experiment, and our Italian colleagues as well. Here we see that microtubule area fraction as a function of time depends on the frequency of the terahertz radiation. It seems to be most effective at 0.5 terahertz next to broadband, which, broadband, yes, broadband is the most effective overall, but then 0.5 terahertz does a better job of destroying microtubules than 1.5. This is still, as I say, preliminary. We've just written up a paper on this and we'll be submitting it, but this area is far from being completely understood. We believe that hydrogen bonds binding tubulin dimers in a microtubule are destroyed by exposure to terahertz, but the radiation itself is absorbed by many different modes, and we need to get to the bottom of it. And I understand that Dr. Cifra's group is working on this as well, so I'll be very curious to see if we can learn more from that. Okay, so these are the terahertz experiments. Then we will, in the final part of this talk, I will focus on other effects, namely responds to electric fields, AC electric fields, and DC electric fields. And so microtubules being so largely endowed with electrostatic charges, they will obviously respond to electric fields in solution, but the fields are screened, and so there's a lot of complication. It's a many-body problem using the language of condensed matter physics. These were experiments done in 2007 by other groups showing realignment of microtubules in the presence of fairly large, actually 4,000 volts per centimeter fields. And this is from another group. You can see here microtubules gliding and sliding and aligning in the direction of the electric field. So there's evidence of this, and that's 50 volts per centimeter, it's a bit smaller. Well, we used even smaller fields and measured electrophoretic mobility in fields at as low as 6 volts per centimeter or so, and observed the movement of both tubule and microtubules in the direction of positive electrode. But there's a twist. We went further. So this was predictable, of course, that these objects will move towards the opposite charge. But we also manipulated the solution. As again, I want to emphasize the importance of the buffer solution, and changed the pH value first. So at pH 5 and lower, actually, what happens is the opposite happened. The mobility reverse direction, and the zeta potential, which was measured with the zeta sizer machine, also showed the reverse charge. In other words, at and below pH 5, microtubules change the electric charge. So that's an isoelectric point, and below 5, they become positive. But this happens also with other solvents, not just pH change, but also DMSO. So DMSO here, you can see here sorry, that's still pH. Yeah, pH dependent. Much more clearly, you can see here at about 5, when the curve crosses the 0 point in the mobility, electrophoretic mobility, and maybe 4.5, something like this, and zeta potential also. But also DMSO at very high concentrations, maybe 85 to 90%, the reversal of the sign occurs as well. So that's interesting, although that's a very high, normally you don't use this high concentration of DMSO in experiments, but it can be done. This is showing that water doesn't have any measurable effect. Glycerol was next. Makes it very sticky, of course, but there's no change of the electrophoretic mobility. Some other ones, other solvents like MES, pipes, and citric acid show some of that as well, especially the citric acid case is interesting at about pH 4, and MES close to 5. We also observed aggregation of tubulin due to DMSO concentration using DLS dynamic light scattering measurements, formation of aggregates, maybe not microtubules, but tetramers perhaps. And now let me try and shed some light on all of this using modeling. So we've done modeling using Poisson-Boltzmann equation with some corrections to the Poisson-Boltzmann corrections to look at the ionic charge distribution around microtubules as a function of ionic concentration. So this is the Poisson-Boltzmann equation in cylindrical coordinates, because that's the cylindrical structure of microtubules. We modified it for variable permittivity, the so-called Booth effect, and also for the concentration effect in the dielectric constant. And I'll show you the results. These are the results just published in Frontiers in Biophysics. And what is interesting is that these dependencies of here you see the local potassium concentration. I told you that we experimentally tested very low and very and physiological, so something like 4 and 80 millimolar concentration of potassium, and here so on the vertical axis you see the local concentration around 3 different aspects of microtubules. The lumen, so the interior of a microtubule, which is supposed to be neutral or empty. Nobody knows what's going on inside, but definitely there is a gradient of the concentration taking place. Then around the C-termini, which I mentioned to you in the beginning, and then around the outer surface, cylindrical surface. And in all 3 cases, there are differences. And you see here the radial position, so distance in nanometers from each of these structures, is one of the axes in the plane, in the XY plane. The axis, the third axis is the bulk concentration of KCl in millimolars. And you can see how dramatically it changes as a function of concentration. This is logarithmic scale. Right, and a lot of information here, so I'll zoom in on some of it. And so this is, for example, showing you the lumen itself as a function of distance, nanometers, from the surface of the lumen. At different concentrations from 10 micromolar and 10 millimolar bulk, outer surface, C-termini. And then on the right, you see the number of bound ionic charges on each of these surfaces as a function of the bulk concentration. And something dramatic happens at around 100 millimolar. It's fairly constant down to 10 millimolar. But then at 100, which is now, remember, that's physiological, there's a dramatic drop. And here's the sort of the summary of it all and a take-home message. Microtubule conductivity, based on these results, you can enter into the conductance equations depending on the, and capacitance as well, by the way, depending on the size of the ionic area surrounding it and the concentration. Conductivity in Siemens per meter here around microtubules crosses over compared to the bulk solution at about 100 millimolar. So for ionic concentrations below 100, microtubules are more conductive than the bulk solution. For solutions with concentration of ions greater than 100 millimolar, the opposite happens. The bulk is more conductive. Very interesting, because this could be a tipping point. Cells may direct electrical signals through microtubules as defined pathways. If they choose to do so, they could lower the ionic concentrations from below 100. And remember, in cancer cells especially, this is the case, much more than 100, down to 5 or 30, between 5 and 30. So in these cancer cells, sorry, I'm talking about the transmembrane potential, but that translates into ionic concentrations, which will be lower. So that could easily explain constancy of signals, sending signals to proliferate, to divide, and so on. I'm not saying that explains cancer, but I think that could be one of the potential implications. Very quickly, we confirmed the ionic and positive charge aggregation around microtubules using a probe, which recently discovered in the group of Professor Meldrum, P4VB, whose structure you can see here. And P4VB is a reporter of local pH, and luckily for us, it binds to tubulin, and the difference between the absorbed and emitted wavelength gives you quantitative measure of local pH, can be calibrated, has been, and I'll show you, this is showing you different wavelength, illuminating this sample with P4VB bound to microtubules. You can see here microtubules re-emitting different wavelengths. And this is the result on the right. You can see here that the concentration of local pH concentration on microtubules is typically about 1 log or factor of 10 greater than the bulk solution, starting from about 6.7 pH 6.7 or so, up to or below that value. There's not much of a difference. And I think this is the final set of experiments which are still unreported. Very intriguing. I would like to sort of throw this into the audience for comments. Interesting experiments performed by my collaborator, Professor Aristide Dogariu at the University of Central Florida, showing delayed luminescence. So 4-minute illumination of microtubules with about 650 nanometer wavelength. These are the intensity is actually quite low, comparable to normal sort of sunlight exposure. And then the cycle of about 10 minutes or so without illumination observation. And these are the results. So the interesting thing is that there is a delayed luminescence, the re-emission of light from microtubules and also tubulin, but more dramatic for microtubules over minutes. As you can see here, 1 minute, 2 minutes, up to 10 minutes, maybe 15 minutes altogether, and 4 different wavelengths were probed. So this is not what you normally expect from such materials, and we are scratching our heads. The only sort of potential candidate amino acid that may be involved in such a thing is tryptophan. And tryptophans form networks on microtubules, 8 tryptophans per dimer, but they are excited by a much lower wavelength or higher frequency than the ones tested. So this is a network of tryptophans forming this kind of lattice with distances within 1 to 1.5 nanometers, so they can be excitonic transfers between them. This is somewhat similar to photosynthetic chlorophyll kind of aggregates, which I think there's 7 in FMO systems, which were so famous not so long ago in regard to quantum biology. Tubulin also has these tryptophans, but of course the lifetime of these re-emitted photons is just mind-boggling. So we've started developing a model based on accident hopping, and corrected for various electrostatic properties of tubulin that we know quite well, and we obtained eigenvalues in such a system in the range that is observed, but we still don't know how to explain the lifetime, and the time for re-emission, which is so long. In the interest of time, let me just skip through this very quickly. I'm almost done. I just want to show you one more interesting experiment from the same group of Professor Dogariu at the University of Central Florida, where measurements of microtubule polymerizations were made in the presence of electromagnetic fields against 650 nanometer exposure. And this is the influence of microtubule polymerization. And that's the bottom line here. You can see in red the density of microtubules as a function of time. And this is again almost an hour and 40 minutes experiment. And black is the control, no field. And you can see here that onset of polymerization is much lower in the presence of these fields. The growth is slower, about 15% lower slope, and a smaller number of sites where microtubules are polymerized, and overall fewer microtubules and less tubulin aggregated together into microtubules. So very interesting effects. We're just scratching the surface, trying to understand various frequencies affecting microtubules. And I have two more things to show you, and that'll be it. Very recent, unpublished, mind-blowing to some degree experiments on cancer cells. These are HeLa cells which are exposed to electric fields. This is cervical cancer HeLa cells with GFP labeled tubulin. That's control. You'll see cell division. This is about 90 minutes compressed to a few seconds. So just beautiful dance, symmetrical ballet, two daughter cells. You've seen this probably, something like this, many times before. Okay, but now, and so this was standard. Now it's something new. This is the same thing in the presence of electric fields, 100 kilohertz. Oh, sorry, that's the same. Here it is. 3-hour exposure to electric fields. So far, so good. Now you see microtubules in green. They don't want to let go. The two cells are linked for more than an hour, I think. And somehow this cleavage furrow is not properly separated, and they cling on to each other. And very briefly, just to summarize, we found, and this is orientational along one axis, we found 3 groups of cancer cells, some which were not affected, about a third which were delayed in their cell division, like this one. Instead of 90 minutes, I think it took like 4 or 5 hours for them to divide. And then finally, the last group, which didn't divide, they actually committed suicide. They went apoptotic and died. So there is definitely something interesting happening with electromagnetic, and perhaps magnetic fields affecting living system structures, and microtubules somehow play a central role here, in my opinion. So that's basically all I prepared. I want to conclude with the richness of electromagnetic behaviors for individual microtubules, which could be used for nanotechnology of the future, I think, and then also effects of electromagnetic fields and polymerization. And finally, with these 2 slides, there is something definitely worth exploring with electric fields and novel cancer therapies. And the company from Israel, Novokira, I should mention, provided us with the device. They implemented this in the clinical setting, but the mechanism is still under investigation. So thank you very much for your attention, and I will be happy to answer any questions.
Thank you very much, Jack. A really, really fantastic talk. I really enjoyed that, particularly the updates I was not aware.
Thank you.
So that's really, really great. So we have a couple of questions so far in the chat. So I'll take the opportunity as a chair to start it first in the row, which is mine. I was curious on the impedance of microtubules in in electrolytes in general, and BRB in different concentration of pipettes. So I know these are just like you do not let's say extract the permittivity and let's say effective conductivity, but you measure impedance and capacitance. So therein there is also an effect of electrolyte interfaces. So I don't know if you consider these.
Yes. We did that. So the paper gets into it because yes, there is definitely contacts and a lot of electrical effects due to the interfaces taking place. So this is where we do the control, and that was constructed in the model, simple model. That yes, thank you for this question. But yeah, it took us quite a long time to extract the signal from noise and the actual information about these. And in fact, I'm still struggling, to be quite honest, with modeling the meshworks as electrical elements connected in sort of quasi-random way. And there's very little in the physical literature, believe it or not, on such things. There's a lot of series and parallel capacitors and resistors and all that, but very few random networks or scale-free or things like that.
Yeah, that's definitely interesting. I can imagine, because usually engineers do things which are, regular or at least somehow predictable.
Yeah.
Okay. So I
And
also want
yeah,
one
sorry.
more there. That we observed in multiple effects in our lab that microtubules, well, one tubulin polymerizes to microtubules, it changes the viscosity, at least effective viscosity, the upper end one, the bulk one. So that definitely should also influence the conductivity of ions in bulk, right? So ions should slow down, so probably the conductivity should be lower. So have you observed something along this line? I mean, if it somehow fits into the picture of the otherwise very, peculiar data, but very nice explicable by your models, which I appreciate.
Yes. Well, we haven't measured viscosity. I would be very keen to see your data on this, because that definitely is part of it. We listed in possible mechanisms viscosity effects, and obviously if you create an exclusion zone of either attract ions and prevent flows or expel them from the vicinity, this will affect the rest of the sample to some degree, and lots of microtubules in the sample, these effects, I'm sure, play the additional role. I wasn't able to extract how much of it is due to viscosity and how much to just forming obstacles, how much, so there's at least 4 or 5 different effects, taking place. So it's a complex system. It's unbelievably complex.
Totally agree. So next question is by Felix Scholkman. Felix, can you, if you like, unmute yourself and also appear if you like, if you ask yourself. You're still there?
Yeah. Do you hear me?
Yeah, we do.
Hello, Michael. Hello, Jack.
Hi, Felix.
Nice talk. I was just curious about the DMSO, because there are some empirical indications that DMSO has also some anti-cancer effects. And if this is maybe related to changes of the biophysical properties of tubulin, actually.
Well, it's a very good solvent, as you know. We didn't expect what we saw, but of course it's a high concentration of DMSO, and if DMSO changes tubulin interactions, including some form at low concentration of DMSO, relatively low, 20% aggregation of tubulins into not microtubules but smaller clusters, oligomers, that may be the case. I mean, whatever you do with microtubules or tubulin in cancer cells to mess them up, you're doing something right. So DMSO may indeed prevent proper formation of microtubules in dividing cells, including cancer cells. So that might be an interesting idea. Mm-hmm.
Yeah, interesting. Yeah.
Yeah, I never thought about this, but because traditionally you think, well, it's done in the lab for experiments as a good solvent, right? Something which is not very soluble, like colchicine, some drugs, you put them in DMSO and then you add that to the solution. But that direct effect on tubulin is definitely there. Thank you.
So we have more questions coming. So I don't know who's first, but let's give a floor to Babak Minafar. If you can unmute yourself and ask a question.
Thank you very much for a very excellent talk. There were a lot of experimental things that it was really amazing. Concerning to the modeling you introduced, it was based on the dielectric constant. As you already mentioned, that they are hydrogen bondings, they are interaction of the hydrogen water with the protein or in the system, they are important. Then you have the lack of those implicit way of the treating the water in your model. Can it be describing fine? And I have also, after finishing I have one comment too.
Well, of course, yes. Your question is very good, and I wish I could do something like explicit water simulation, MD. You know, that is something that is vastly superior than our phenomenological, you know, Poisson-Boltzmann approximations with various dielectric constant approximations. So I wish somebody could do this. It requires, you know, major computational effort, and we haven't had time to do that yet. Maybe somebody else can do it. And yes, so organization of water, that brings the question of I don't know if you are also implying easy water of Jerry Pollack, you know, these kinds of things. I didn't want to tell you this, but we also did experiments on conductivity in these solutions with the presence of light, laser light, and it changes. So I'm not ready to present the data, but I suspect that this has to do with easy water because you know, if you listen to Jerry Pollack or read his work, he talks about non-equilibrium situations where electromagnetic fields energize water and form these exotic structures. So yes, that's definitely part of it.
And for this one, I want to, as you said, for MD simulations, I would like to introduce some of the work of my colleague, Sarah Harris. She is from University of Leeds in UK, and she is doing multi-scale simulation with fluctuating finite element analysis, which those data are coming from cryo microscopy data. Of course, after that, maybe this can go in future to the explicit system, because nowadays they are treating as a medium, but later on maybe it can go to the coarse graining simulations and later on to the MD simulations.
Great.
It can be very good cooperative work with her.
Yes, very good. Thank you for I made a note of this. I will look it up. This is super interesting. Yes, thank you.
So, thank you for a question and answer. So now, Rod O'Connor, Rod, are you there? You can unmute yourself.
I'm here.
Hi.
I'm over illuminated. Sorry. Thank you for that fantastic talk. I really enjoyed that, seeing that all together, and I've never had the pleasure of seeing your presentations before, so this was just great. My question for you goes back to really early work you probably maybe have come across by Kenneth Cole in Woods Hole, who did these recordings years ago in 1940s, who came up with all the Cole model and all sorts of fantastic stuff before Hodgkin and Huxley. And he measured inductance in axons, in the squid giant axon. And this was measured, and then it sort of went away, and they talked about it and disappeared. And these are unmyelinated giant axons, right? So I wonder if it has to do with the preparation that they did, because I know in Woods Hole classically they would take a small device like a lawn roller that you use to flatten your grass, and they'd squeeze out all the axoplasm, right? So they would remove a large part of this, but I wonder whether it wasn't incomplete or not, and that they had some in there. So I wonder if you've ever thought of going and measuring this in the context of a real nerve in
Yes.
I know your paper by, I think was it Friel or Priel, one of your students, showed the transistor behavior of these sort of bundles of microtubules.
Yes.
Clips. Yeah.
Well, in fact, we planned to do this. We applied for some funding to the Human Frontiers along exactly the lines you described to do these measurements on live neurons and axons in particular. We didn't get funding, so everything, as you know, depends on the availability of funds. But yeah, that would be a logical extension of this, and I suspect that that there is I'll look up the paper you mentioned by Kenneth Cole from 1940s. 1940s. And see if we can.
There's a few. He actually reported a difference between axial versus transverse measurements And he had one of the very early versions of the like HP network analyzer, like version 1, I think. So I'm sure Mikhail could do much better measurements these days in his lab with his equipment. But this could be something we should think of as trying to measure maybe together or in nerves. If you can't get a squid, because I know in Edmonton you don't have a lot of squid.
No, no.
Yes.
In fact, you know, I wanted to, because we have a small amount of funding, but we are not experts in neurons, and cancer cells are available at the Cancer Institute, so that's why I'm working on these HeLa cells. But I definitely would be interested. Please, if you could please email me, then we can maybe talk offline about this.
Let's do that. Thank you very much.
Thank you.
So, any more questions from the participants audience? I have one more, actually two. One question, one comment. So I'm wondering, you know, exactly what you pointed out on the terahertz. So we are just having this large funding on a sub-terahertz, well, chip devices, which will enable us to see what happens with protein structures, protein nanomachines, including microtubules and motor proteins, when we will be applying very intense electric field. Well, intense by getting it, you know, by localizing it on the chip. So that's the advantage of chip. And while seeing on microscopy how the things work. So this is definitely something very interesting and very current thing for us. So I was wondering about the parameters that you mentioned. So was it really like 20 minutes train of the, okay, so it was like rather long exposure to see some effects. Okay.
Yes,
okay.
yes. But non-thermal. There was no heating because of the millisecond separation. Yeah.
So okay, so the well, and the train was, and how long the pulses were themselves?
Picosecond pulses and millisecond gaps between the pulses.
Okay, so it was single picosecond pulse, then a millisecond gap to get this. Okay, that's really, should be really non-thermal, even though the fields are very strong. It's very interesting. Okay, and there,
in fact,
yeah,
we had problems with the intensity of these fields because we never reached, not always reached the required minimum 500 kilovolts per centimeter, typically 250, 300, something like this.
I see what you mean. We are just struggling with the similar things for pulsed fields here, for a nanosecond pulse. Okay, and there for the filtered terahertz, so let's say applying particular frequencies, did you observe something like reasonably, let's say, believable frequency dependence? You know, I'm trying to address if there are any observable resonances or not that clear.
Well, I think we didn't span that big of a frequency range, you know, from 0.5 to 2.5. Right. So I wouldn't say that there is dependence. I don't know. I think there is some. You have to have enough energy to break, in my opinion, the hydrogen bonds. So, but that, yeah, there's a lot of bonds, so that's why it's taking a long time.
Okay, I see.
In fact, if you don't have enough energy, they may reconstitute themselves. I think you move the atoms apart or twist them, and then they come back together because of the potential that traps them.
Okay, I see. Yeah, well, that's the rate of, let's say, disassembly to the kind of deconstruction or destruction has to be faster than the reassembly, right?
Exactly.
Okay, maybe I have one more comment on the very last part of your talk. You mentioned the delayed luminescence. So we have quite some experience with the measuring, weak fluxes of light. And typically the delayed light is a nuisance for us because it takes a very long time for various materials. So for me, it's not particularly surprising that something can afterglow even for, even after simple light illumination in the lab for like even hours. I believe there are definitely at least two classes of effects, physical and chemical. So if something is rather inert, it can be really some strange trapped states, which could be very interesting for particular physics there. But in water solutions exposed to air, even for the light of 650 nanometers that you mentioned, even the light is not that strong. There can be this can trigger oxidation. It was shown that even near infrared can trigger oxidation effects. So basically, the light can trigger chemistry, which then slowly fades out.
I see.
So that's something which we found as as an effect. It can be an effect which is useful, or it can be confounding factor depending what you are looking at. So this is something which came to my mind when I see the data.
I will want to talk to you about this, Michal. Not now, of course, but
sure. When you come to
maybe
Prague,
we can set up a separate call about this.
Like that. Yeah, sure, definitely, it would be interesting. I'm pity that Philip Kurian is not here. He'll be definitely interested, but he will at least see this on YouTube. Once it's online, I will prompt him. Because he's really interested in these excited states, propagation along the microtubules. So, okay, great. I'm just seeing if there are any more questions in the chat. I don't see any raised hand either. So, yeah. Thank you so much. We run out of time, so we will respect all the time abilities of other people. So definitely, Jack, we'll keep in touch. I think we can make a separate calls on other things. So
later today.
Great. So thank you everybody for joining. Thank you, Jack, for being with us rather early morning. Depends on depends on the approach to the working day. So thank you very much, and hope to see you on next webinar. So everybody will be updated. Whoever attended will be also in the mailing list, so we will be keep up to date. So Jack, thank you very much again.
Thank you. Bye-bye.
Have a good day.
You too.